Hello, everyone, and welcome to Code with Italian. Sorry for the small spoiler there, and also Ivan was missing. He had to
No,
have
I'm
his
here.
WWE entrance.
Pa-pa-ra-pa.
John Cena.
I was just closing the window just to have it a bit quieter. Jesus Christ, we are.
Sorry, the trolling has
Uh,
already started
He's
here.
a true professional. He knows how to make an entrance. I should learn
Yeah,
from him.
Sure.
perfect clip,
Thank,
Ivan. Perfect
thank you, thank you, thank you. This is the perfect shot. So,
So, first of all, everyone, welcome back. It's been a few months. It's been a very busy few months for all of us, even though you probably assume we were on the beach chilling. No such thing has happened,
I'm sure. Look at,
unfortunately.
look at me. I mean,
Yeah,
I'm the so tan. That's the,
you are
that's
reflective.
yeah, yeah. I mean, that's how I roll.
Okay,
Anyway,
so we are back with someone you've probably seen around here before. Hi, Roman. Welcome back.
Hey, happy to be back.
Yeah. So today we get to nerd out about Kotlin performance, micro optimizations. Uh, you've written some blog articles about the topic, and I'm curious to see. Like I've read some of them, not all of them, but I'm here to learn what I didn't read.
Yeah, and hopefully I'll remember how to teach that.
I'm sure we'll figure it out. And worst case scenario, we can always rewatch it at like 0.5 speed.
It's not that bad. It's one of those things that's that looks more scary than it actually is.
yes, sure.
Come on, Ivan, you're writing compose code these days, so you got to
Yeah.
learn the tricks.
No. Man. I'm here for this. I'm very excited, and preemptively, I say that, okay, I'm probably gonna get the like 15% of the stuff, but we have recording on YouTube, so that's the
That's the
that's the beauty.
spirit.
Plus, I'm gonna just do the shorts. So basically I'm going through the video a couple of times to pick the shorts. So something will stick. Don't worry.
I just do what I do, pretend you understand what's going on.
Yeah,
That
sure. I
always
mean,
works. Just
that's
nod.
uh
Like,
huh.
hmm.
Sure. Like active listening, faking active listening.
So, before we get started with the Kotlin performance, Ivan, do you want to do your thing and talk about the giveaway?
Yes. So we are giving away tickets for conferences. London, I guess today we have.
No,
Uh,
Italy?
Italy.
Yeah, I think we did
Whatever.
London. I need to check. I don't
It's not quite the
remember.
same.
It's the
Yeah,
same
I
thing.
mean, it's pretty. So if you like droid guns and you want to come to Europe or you want to travel in Europe, we have tickets for Italy. We have the online ones, and we also have probably one
Yes.
in person.
We
If you
have 2 in person and 5 online.
Okay, so stick with us during the live. We will give away at least a few. I don't know if you want to do it also on YouTube on the social, but stick with us.
Yeah, maybe let's keep like 2 of the online tickets for YouTube so people
Yeah,
that are not watching live can still get
yeah.
something.
And because I broke the software that we wrote for picking the giveaways today, I just went to my D&D stuff. So we have a D20, so I'm gonna use this
So now we
to.
need 20 people.
Well,
Otherwise,
no, I'm gonna do some.
your
I'm
system
gonna do
doesn't
some.
work.
No, but now I'm probably gonna do some, modulo something, and then I'm gonna just pull it off.
You're
Don't
gonna
worry.
science it, I see. Yeah, yeah, yeah.
Yeah, but the randomness is gonna be there. I mean, there is nothing more random than this shit. So yeah, and as of course you saw the link in the chat. If you want to support us for free, you can connect your Amazon subscription to your Twitch account, and you will see that you can subscribe to one channel every month for free. You can pick us, you can support us. We are printing stickers and other stuff that we give away at conferences and during the streams. So if you want to, get any chance to get like a keychain or something, please consider subscribing either as a coffee subscriber or get something on the merch store if you like the t-shirts, and we have a lot of stuff that you can pick from. And you can also, again, subscribe for free if you have Amazon Prime. So let's go, because I have a sneak peek of what we will be sharing on screen, and the thing is getting uncomfortable. The amount of videos is getting uncomfortable already. So please.
All right. Yeah. So some context. We've been working on Compose for a while, and once typical software development, once you have something that works and it's being used, at some point you have to worry about performance. Of course, you should always worry about performance, especially during the design phase. But when you work on something like a library or a framework like Compose, the way Chet used to like to say it is that we're the inner loop of the application. So anything that the library or framework does that you don't need is going to impact the performance of your app, right? So it's kind of on us to try and optimize as much as we can from the library so that you can make your own performance mistakes and your app will still behave nicely. So the kind of stuff that I'm going to talk about today, you probably don't need to worry about like 99% of the time. But if you ever find that you're writing performance-sensitive code, and it could be, like heavy file processing, I don't know, I saw PY yesterday was blogging again about the kind of like graph traversal that he does for his leak canary detector. It's the kind of code that you really want to go fast. So it's the kind of skill that's nice to have in the back of your mind, because someday you might need it, right? None of what I'm going to show, none of it, the point is to say like, hey, in your button listener or your view model constructor, like apply all those techniques, right? Like that is not the point. And of course, like even when you understand like the kind of optimizations you can do by looking at the compiled code, you should always have benchmarks for a couple of reasons. A, to measure the actual impact, in the real world, but B, to also make sure that you don't regress on your performance optimizations. So on Compose, our performance team has built this really awesome benchmark system in our CI where every time we make a change, we run our benchmarks and we get bugs that are automatically filed whenever there's a positive or negative regression, which means that if we make performance worse, we know like which changes may have caused this. But if we make performance better, a bug is also filed, because we want to make sure that we understand why performance is better. Like, is the benchmark wrong? Did we do something on purpose or not?
Oh, nice.
So it's kind of nice. At first, I was worried because I was doing my optimizations and I was getting those bugs. I'm like, oh crap! Like, it's not working. Like, I made things worse. And like, I look at the benchmarks, like, no, it's faster. Like, okay, we're also finding bugs because things are getting better. So that's really nice. And it's interesting, right? Because some of the changes that I made and other people on the team have made, like, they're really micro optimizations. We're talking about shaving off a few instructions. But when you do this, and it's code that's invoked by the layout code, the measure code, the draw code, the input dispatching system, things that happen all the time, once you benchmark like at the scale of an app, the effects are visible. And more importantly, like once you start panning up those changes, like dozens, hundreds, thousands, you get like really, really important benefits. So make sure that you do this when it makes sense for you. Make sure that you benchmark and measure, but it's also just interesting to know how this works. Actually, I'm going to start by showing you. So I have a window on screen, if we can bring it up. On the screen.
It's on now?
Yeah, okay. So recently, it's actually super timely. The system health team on Android, so the team that looks at the performance of the entire operating system, has been working with the art team, and they added support for Kotlin, Java on Android, R8, and Art to this online tool called Compiler Explorer. So it's godbolt.org, named after the guy who created at Godbolt. And this is a super popular tool, especially among C and C++ developers. You can see here, I just opened the page to show you. And that's code I wrote a few months ago, and I was looking at what Clang, the C++ compiler, generates for 64-bit ARM CPUs, because I wanted to see, like, if the code was performant.
Can you zoom in the page a bit, because it's a bit small? I'm sure people
Yeah,
will
sure.
ask.
Yeah, we don't have to. We're not going to look at this page a lot. It's just to let you know that it exists.
Yeah.
So if you go to templates at the top, now you can choose Android Java ID or Android Kotlin ID. So if you
fancy.
Android Kotlin ID, it presets up everything so that you can write your own baseline profiles, you can write your own ProGuard configuration, and you can write code. And whenever you type code, let's say that our square function, instead of a square, we make it a cube. Wait a little bit. On the right side, you will see the output of the compiler. You can choose the compiler here. Here, it's using the compiler that converts DEX to OAT or OAT. So OAT is the format that's post-AOT. So once we compiled your DEX code to the machine code that the CPU understands, you're left with this OAT file. So this shows you more or less, I'm not going to go into too much details, but basically after the JIT or after the AOT, that's the actual machine code that's going to run on your Android device, right? So if we look at square function, that's now a cube, we're multiplying the parameter by itself twice. And if you look at the assembly code, we see two multiplications, which is exactly what we would expect.
Can I ask a question?
Yeah.
As far as I remember, in Kotlin Explorer, you have to have a physical device attached to get the AOT output. How does this do that without the connected device?
Right, so we'll talk about what Kotlin Explorer is in a little bit, but you can see here, so that's a host version of DEX2OAT, and you can see at the top, it's telling you that it's targeting an F53 CPU, and here it's saying that some of those features are not supported by the target device, which is a generic device in this case. So for instance, minus FP16 means it doesn't support half float, 16-bit float, or it doesn't support the dot product in the CPU. So that's the thing with this compiler explorer. You can pass options to DEX2OAT to set those flags, but this is not necessarily what your device is going to do. And it's one of the reasons why I prefer to use my own tool that I'm going to show. The other reason is that it's a bit slow because it runs, in the cloud, like it just took like 15 seconds to compile this method.
Yeah, that was my question. This thing is running on somebody else's server, right? Or it's not running in the browser with something fancy.
As far I don't know. I should look at the source code some more, but yeah, either it's hosted somewhere or it's running maybe with Wasm. I assume it's hosted somewhere in the Docker image. Yeah. Anyway, and so here you can choose your compiler. So you can choose to run just R8. You can look at D8. So if we pick D8, we should see the DEX code, not the ARM assembly code that ends up on the device. Anyway, so it's super useful because that tool is available in your web browser, so very easily accessible. Yeah, here's the DEX code, the current DEX code for what we are doing.
Cool.
The other cool thing about this tool is that you can share. So you can generate a link, send that to someone, they will see the exact same view that you have. So super useful, like on a team, once you've found an optimization, you can send the link to someone and say like, hey, look what I've done. We should talk about it, like should we take the change or not? That said, so Sebastiano mentioned Kotlin Explorer. So Kotlin Explorer is a tool that I wrote that basically does the same thing. Because when I wrote this tool, what I just showed you was available internally at Google. There was someone's machine somewhere on the network was running it. But I wanted to have something available offline. So it's on GitHub. You can download binaries for macOS. You can, I think Linux as well. Yeah, macOS and Linux. Windows should work, but I don't have a Windows machine to test with, so try it on your own. And it's basically the same idea. It's written in Compose for desktop, and we're going to be using that from now on. So I'm going to switch my screen to a different window.
Sebastiano, before you even say it, yes, I'm gonna run it on Windows to make sure that it works.
I wasn't gonna ask.
Yeah, come on, I don't believe you. I mean, never I was like this close.
Probably I wasn't gonna ask.
Yeah, sure. Anyway, I gotta give it a try.
All right, so let's see. Presentation mode. Okay, so that's the tool. When you run it, you can type Kotlin code on this side. So we're gonna do a square function. Then you need to have an emulator or a physical device connected. So currently I have a Pixel 6 that's connected to my machine. And when you click build and disassemble, it's gonna compile, send the DEX file to your phone, to your device, disassemble it on the device, and then, I forgot this annotation, we'll talk about this. And then you're gonna see the output of the compilation for that device.
Nice.
So it's a bit different from what I just showed you on the web because I do like more specific syntax highlighting. I clean up the output. It shows you the number of instructions. It's also faster because it runs locally, and also it shows you basically what's going to happen on your device. You have some control if you go to the preferences. You can set up the ProGuard configuration. You can set up the Kotlin compiler arguments. And by default, there will be in the menu. Oh yeah, you don't see the menu, but in the menu bar, you can enable or disable optimizing with R8. I recommend that you do whatever that you're doing, in your app. If you're not using R8, turn it off. If you're using R8, turn it on. It's very interesting to compare.
But also, if you're not using R8, turn it on in your app.
Yes.
Especially if you're using Compose.
No, and it's actually what's nice about a tool like this because you can see what R8 does, and you might be really surprised by the kind of optimizations that R8 will do for you. There is another option for R8 to say keep everything. So if you turn on keep everything, we're going to tell R8 do not remove any code from the output, right? So if I keep everything here, the square function is going to be compiled. You see the output. If I don't keep everything and I compile, that's what happened the first time. It's going to be empty because R8's like, well, you're not using that function. I'm just going to get rid of it.
Fair enough.
So if you don't keep everything, the tool has an annotation add keep that you can put on one you want to keep, and that's going to keep the code and you can see it. You have to be careful. Yeah?
Sorry, there's a question from chat, which is, can the device be connected with Wi-Fi? I guess wireless ADB is what they're asking.
Maybe, I don't know. Honestly, the tool is pretty dumb. Like all it does is it calls ADB from the shell. So I don't know. Maybe it works. I've never tried. Yeah, probably. Try it. Let me know if it works, and if it doesn't, file a request. Or an OITOR, yeah. So with the keep annotation, we have to be a little careful because if you keep something that would not be kept in your app, there might be optimizations that R8 won't do that would be done normally. Another thing you can do with this tool, you don't have to look at just the ARM assembly code. You can also look at the Java bytecode and the DEX code. So again, there are menus at the top where you can turn that on or off. So if I recompile this, we're going to see, okay, so this is the Java bytecode that was generated by Kotlin C. This is the DEX code after converting to DEX, and then you have the ARM assembly code. So for something as simple as squaring a number, basically all three languages look very much the same. It's like we multiply a float and we're done. The output can look widely different for more complex operations. I find most of the time I just look at the ARM assembly code. I find it useful sometimes to look at the DEX code because the ARM assembly can be very difficult to understand at times because it's so low level. So looking at the DEX can be helpful to get a better high-level understanding of what the code is doing. And then when you look at the ARM assembly code, you can kind of like guess at some of the operations. But we'll get back to that. One last thing, if you want to test locally, if you add a main function, you can run the code. So that's going to run on your machine, on your desktop. You're going to get the output at the bottom. This is also where you're going to get the compilation errors. And that leads us to one last feature. So here on the right side, when you click a line, you're going to have a little help here that's going to tell you.
Nice.
Give you the
It's
right.
actually nice.
So this is. Yeah, go ahead.
So, and where do you get the documentation? Is it like a, you are
Yeah,
fetching it, or is it embedded?
It's embedded. It was scraped from the ARM website. So the website I showed you, Compiler Explorer, does the same thing. I actually got the idea from them. So you can download a giant XML file and then just generate a piece of code that embeds the documentation. You just have to know, and here at the bottom, you can click a link that will take you to the documentation online. This is a best effort documentation because ARM assembling being what it is, when you have an operation like multiply float fmul, depending on the arguments and how you pass them, the actual what the function does can be different. I'm not trying to decode that, so I'm basically picking one of the fmul because fundamentally they all do a multiplication of floats. Here they multiply registers, but if that was something like this, that would mean like multiply this register by the value at this address offset by some other register. I'm not trying to decode that for you. You just need to send some multiplication, right?
Just to give you like an idea of the...
Right. And sometimes it's right.
I love your confidence. Sometimes.
Yeah. And the link to the documentation, same thing. The ARM links don't really have, are not, they're kind of random. So it tries to build the right link, but it doesn't always work. So it might work, might not work. When it fails, it takes you basically to the index page, and you can find the operation yourself. So given all that, let's look at some code. And let's start with something. One of the very first things I did with this tool, and I'll show you. I'll show you the code. So in Compose, we have this class called offset. We're going to take a look at it. So offset is an inline value class.
Mm-hmm.
If you're not familiar with inline value classes, in Kotlin, there are classes that can wrap a single value, usually a primitive type on array. It behaves like a class in terms of syntax in your code, but at compile time, the class basically disappears and it's replaced by the actual value. So in this case, our class offset wraps a long, so a 64-bit word. And what we want to do with that, we actually want to encode an X and a Y. Those are floats. So 32-bit plus 32-bit, we can encode them in a long. And the idea behind that is we use the offset all over the place in Compose, right? Like all the layout and drawing use offset, they build offset all the time. If we were to use a normal class, we would have to instantiate that class constantly, putting pressure on the GC, paying the cost of running the constructors, and so on. So this is kind of like one of those zero-cost abstractions that exist in Kotlin. And it's actually really nice. It works really well. And this, let me finish writing the code real quick. I'm just going to add this packing helper. I'm trying to bring the code back to how it was when we originally created this class. Then we have an extra function here. Oops. So I'm going to show you real quick. So again, the idea is to like, and let's see if it compiles. Yeah, it's compiling. There's just no main method I try to run. Okay, so again, our goal is to take an X and a Y as floats, and we want to pack them inside a long. So to pack them, we can look at the function here. It's pretty simple. You have a float. There's a method in Kotlin. There's an equivalent in Java called toRawBits. It basically tells the compiler, just give me the float as an integer, but don't do a conversion, right? If my float is 1, I don't want the integer 1. I want the integer that represents the bits of the float. It's literally like, give me the memory of that float. We do that for the two parameters, and then we shift one of them by 32-bit to the left, and then we put the other one to the right. So pretty simple encoding, even if you're not familiar with bitwise operation, it's fairly simple. And then when we want to unpack the values, like in the getters X and Y, we do the exact opposite. So if you look at unpack, we say take the long, shift it to the right by 32 bits, and then we use this float from bit function that says, take this integer as a bit representation, and now give me the float from that memory. So if we compile this and we look at the code, so it looks pretty simple, right? Like you have your X and your Y getter. We do one extra thing. We say, hey, if this offset is unspecified, so unspecified, is like not a number in both X and Y, we'll throw an exception. That's a built-in Kotlin function. Otherwise, we're going to return the actual value. So now if we decompile that, it's going to take a couple seconds. All right, let's look at our getX function. Oh yeah, here you go, getX. So it has 50 instructions and 4 branches. So this is all the code that's going to run every time that we want to access X or Y.
Damn.
Which, right, I don't know about you, but like, my initial reaction was like, wait a minute, we do this everywhere. We kind of want just to return, like the code I would expect is just like a shift and maybe a cast. That should be about it. Instead, we have all of this. And one of the reasons we have all of this, like that's where like the first times it might be easier to look at the DEX. So if we recompile this and look at the DEX bytecode, it's going to get a little clearer what's going on. So if we look for getX, okay. So first we load the unspecified object, then we call a function, that does an equality test. We're checking if this equals unspecified. If not, something happens. There's a jump. Here we actually do the work because we recognize the turn the bits to floats. So this is the actual work. And then there's a return. But then there's all that code after the return, right? After we exit the function. So if you look at the branches, so there's this useful feature in Kotlin Explorer. When you click on an instruction branches, it will show you where the jump goes. So you get an idea of like what that does, right? So here we see, what we see is a branch that jumps into that code where we create a new exception instance. We load a string, and then we invoke toString on it, and then we throw the exception. So that's because of that test check. And when you go to the ARM assembly code, all that code that you see is because of that, right?
It's pretty much that.
Right. Then things could actually get worse. If I disable arith and we compile that, right, and I go back to the tool tries to keep the line you were on, but when you change the code dramatically, then it loses track. So if I turn off arith, instead of having 50 instructions, we have 65 instructions and even more branches. And again, to understand what's going on, like we can go look at the DEX code, and this is to me a good example of why you should use arith, because arith can understand things about your code that make sense to you but don't make sense to a compiler. So if we look at the code without arith, you can see that we're calling this method unpack float on this companion object, right? Because we kind of want to have like a static function. So it has to load an object, because companion objects in Kotlin are they're companion object. They're an instance of the myClass.companion. So, and the problem is when you load a static object, that means that you have to ensure that the class has been statically initialized. So there are checks that are inserted in the code in the ARM assembly to guarantee that the class has been initialized.
Yeah, it's there.
For us, it makes no sense, right? Like our companion object is just a bunch of inline functions. There's nothing to initialize. But the JVM or the Java or the art semantics say if you touch a class, we have to make sure it's initialized because there could be side effects. So we pay that price for something that we don't care about. Now, when you use arith is smart enough to see that and say, we don't need any of this. I'm going to get rid of all that crap, and we can save a bunch of instructions. And then you can see, like, even in those methods, right, that I wrote that are inline here, we call float.frombit. The way that's implemented in Kotlin is through another companion object. So there's another static load. So there's another memory access. There's another check to see if the class was initialized statically, right? And we still haven't done the work. All we're trying to do is say, I have bits. I want them to be a float. That's all I want, right? And already we spent a bunch of time, like, all that was completely useless.
Yeah.
Like, that has nothing to do with what we're trying to do.
Like all this stuff in C would be one line of code, right?
So converting a bit to float in ARM assembly is literally one instruction. So none of this should happen. And so when we go back to the ARM assembly code, it's all that stuff. And you can see some hints, right? Like it says here, like P get object static. So all those P labels, those are features internal to art. So this is saying we're gonna call into art. There's some kind of like, runtime method that we're invoking to get the static object at a certain address. And here, like alloc object initialize, we're basically jumping to the piece of code that says, hey, we're after the return function. We're saying like, hey, make sure that the static is initialized, right? Something that, again, we don't care about because we have nothing to initialize. Yeah. And you can see that, after the return, the compiler puts a lot of code. So that code, most of the time, you're not going to run that code. That's an epilogue. Those are kind of like, it's a pattern that you'll see a lot when you look at the ARM assembly code. It's all the exceptional cases, the failure cases. So sometimes, for instance, art will assume that you're not going to have an index out of bound exception when you access an array. But if you do, it's going to jump after the return into a code that will de-optimize the code for the JIT, so you can like run the code again with the bounce checks. Anyway, so most of the time you're not going to jump into that code, so that's not a big deal, right? It's like we're not paying for the code that we don't use, except that we do, because the way CPUs work, I'm sure you're aware of, like caches, like the L1 cache, the L2 cache for data. There's also a cache for the instructions. Mm-hmm. So as you're running through the flow of instruction in your code, the CPU is prefetching what comes next. And once you reach around here, it's going to start prefetching code that you will probably never run, which means it has to evict other things from the cache. So having that code here will actually impact the performance. If you're inside a loop, for instance, it's going to mean that we may have to reload instructions inside the loop and waste precious time because we have to unload the cache and reload the cache. So we kind of want to get rid of all of that. One way we can do it is pretty simple. We're going to first get rid of the companion object. Mm-hmm. Because this is all internal stuff. I can make it, those are public, but we could make them private to this file.
Private functions, yeah.
Right, so it doesn't matter, right? Like I can deal with not having namespacing, not a big deal. So now,
it puts the, let's say the cognitive weight a bit on you to mm-hmm. ease up the compiler, right? Somehow, absolutely, right? Yeah. I'm working in a file. I can probably manage the fact that all my stuff is going to be here, even if I don't have a namespace. Probably I just need to scroll a bit, and the function is going to be there. So
yeah, but now look at that. So we still have array disabled, right? All I did was move those functions to top-level functions. We went from 65 instructions down to 51, and from 9 branches to 4. And branches are bad can be bad because if they're mispredicted, the CPU has to flush the pipeline and so on. So we got rid of one of those static loads and one of those initialization checks. We still have one here because we're comparing to this unspecified constant that's defined inside another companion object. But this is something we could also optimize. Because if we look at this unspecified, right, we're encoding 2 times not a number inside a long. So instead of testing the object, we could look at the value that we encoded directly, right? So we could write the code this way. And let's see if that makes a difference. So we had 51 and 4. It's okay, so that didn't really change anything because it still has to load the static object and then extract the value. So instead of doing that, The next step is you just encode the not a number directly. So that's
which you know by heart.
Yeah, by now I know it by heart.
But it's interesting that the not a number looks like a number, but okay.
I mean, it's still an int at some point, right?
Well,
it's bytes.
Yes. So here, we went from we saved one instruction, and so there's still a get static that's being accessed, and why we have to look at the dex. So let's look at the dex. X. All right, so let's see. Oh, the static is because we still use this built-in float.frontBits from Kotlin. So that here is the static access that's costing us. So here you have two solutions. You can either enable arith, because arith will take care of it, or you can do what we did in Compose. And this is where things become interesting, I would say, because when we optimize the code for Compose, we're kind of in a difficult situation because we have to take into account some folks will use AOT, some folks will be jitted, some folks will use arith, some folks won't use arith. We can't optimize the code perfectly for all those situations. But this is one of those cases where if you don't use arith, we can do this instead. So what I'm doing here is that I created my own function called float from bits instead of float.frontBits. And all it does is do what the Kotlin standard library does. I'm calling the function that's part of java.lang.float, right? And arith has an intrinsic for that. The difference is I'm not going through a companion object, right? That's all I'm doing. I'm skipping the companion object. Now, if I compile that, so we were at 50 instructions and 4 branches, still with the arith off, and now we're at 46 instructions and 4 branches.
You know what this makes me kind of laugh is that you have that inline function, and in the IDE, I'm sure 90% that you would get the inspection that says, oh, this doesn't need to be an inline. There's no reason to make this inline. They're like,
pretty much every file I touch ends up with like a surprise nothing to inline somewhere at the top. Yes, and for the most part that's true, and you have to be careful with the inlining because sometimes you can make things worse. But and arith will do some inlining for you. The arith compiler will do some inlining for you, and sometimes actually I'm fighting them the other way around, where I'm trying to not, and we're going to look at that actually right now. I want them to not inline something because it's important.
Can I ask you another thing before we proceed? So what we had before was the packing helper that was a class with a companion object.
Yep.
If that were straight up an object without a companion object inside, would that make a difference?
I think no, it's the same thing because I forget what it's derived from, but it's still a static access, and I think it becomes a static object as part of a synthetic class that has the name of the file, and you're back to the same problem. But anyway, so now if I turn on arith again, just to see what we get, so we're at 46 instructions and 4 branches, and now with arith, we are at we have 48 instructions. So arith did some extra inlining. That's why the class, like the function grew. Okay, so the next step is we want to make this better, this check. So if you look at the implementation of check in Kotlin, it's actually fairly simple. All it does, I'm gonna write a version, my own version here. So all it does is it's an inline function that takes a boolean and that takes a lambda that returns not a string but that returns an any. And what the code does is basically this: if the boolean is false, throw an exception, and the message of the exception is the invocation of the lambda. So the two things that we are fixing here is, first of all, we are creating a lambda that returns a string, so we don't have to call toString, because if you look at the code, we're calling toString on a string. which is dumb.
Just in case.
Just in case. And then, the throw exception, that's that code here that gets inline. So there's a bunch of instructions that are being generated for the slow path, right? I'm like, this is already the slow path. I don't want that code to be inlined because the whole point is that if I take that path, I'm already screwed, right? But if you inline all that code, like I said earlier, we're going to affect the instruction cache of the CPU.
Mm-hmm.
So instead of throwing the exception directly, we call a function, and all it does, that function throws the exception, right? What we're trying to do here is to say, we're going to inline this, but I want a function call instead of the exception inline. Now, R8 will sometimes happily inline this new function we created. So in Compose, what we did is that we have a ProGuard rule that says, hey, if there's a top-level function that starts with throw, don't keep it, don't inline it. Art will never inline a function that only does a throw. That's a guarantee that Art makes. Is that R8 sometimes is a bit too aggressive. But once you've done that, we can go back to our code, and our check can become our check precondition. And now if we recompile, so we're at 48 instructions.
Smaller and smaller.
Yeah. Now we're at 27 instructions, right?
Oh, wow.
And now it's starting to look a lot better. Look at that. It's like, we can see that we're calling this the function we just created, basically. So the test is somewhere here, and then here we go in the failure mode. Otherwise, we do the actual extraction of the float.
I'm kind of surprised that some of these things are not done in the Kotlin standard library.
Yeah, I think
because it feels like at least the stuff that you're doing for the check precondition, it doesn't look like it should have negative side effects.
The only negative side effect is that in the stack trace, you're going to see an extra level, but it's no different than when you have a null pointer exception. Well, especially because when you have null checks in Kotlin, the compiler does introduce extra, it calls intrinsic.check null.
Yeah.
So that happens already. So yeah, it could be done in the standard library. Now the last thing we can do, and it's what we ended up doing, was, you know what? Those things are never not a number. And if the caller cares, they should do the check. So let's get rid of that.
How to make it easier?
Push the responsibility to the caller. Come on.
Yeah, but just like with floats, right? Like when you use a float, and look at that. Look what happens. Because now we removed enough code that everything fits in the right registers, and we're left with only a right shift. This instruction is actually useless, so it could be even shorter, but that's art doing that, so can't fix that. So we shift our long to the right by 32-bit, and then fmov means convert that integer to a float inside the register, and that's it, and we're done, right? And so now, once you have that, what we can do is also say, you know what? I'm gonna inline this because when you look at the cost of a function call, this is less instructions than an actual function call. So I'm like, let's just,
throw it there.
Right, anyway, and now everything's gone, right? We're left with the bare minimum that we have to do. And surprisingly, so these kind of optimizations we saw in our benchmarks, all of our layout benchmarks came back faster by just doing these kind of changes. And then when you start thinking like that, a lot of things, you can improve a lot of other things. I have other examples here. For instance, is valid. So here that becomes a little more complicated. So we have this is valid function that returns true if both numbers are not a number, right? If you have not a number as X or Y, it throws an exception. So first of all, throwing an exception is probably a bad idea because that means the function, this can only return true, otherwise it throws. So it should just be true or false. And if you look at the implementation, again, it's really big. It's 57 instructions, a bunch of branches. Same thing, we have the exception problem and all that. So we could instead say, okay, return x is not a number and y is not a number. So that's going to get a lot better. Oops, was it complaining? Oh yeah, sorry. We'll remove this one here. All right, so we're down to 23 instructions, which is still a lot because what it has to do, actually, for it to be correct, we have to do this as well. Okay, let's look again. Is valid. Where did it go? Is valid, is valid. Okay, 14 instructions. It basically has to unpack X and unpack Y, and then it calls isNone, which is part of the Kotlin standard library. The way that's implemented on the CPU is actually pretty cool. You can see it here in the code. You can see here that we create our float with this fmod, right? Like that's what we saw earlier. It moves the integer into a float register. And to check if something is not a number, you can compare, so float comparison. We compare the number to itself because always false the test. And so then we say like branch if not equal. So if the test, if the number is not equal to itself, it's not a number. And we do that twice. There must be another, there's another fcomp right here. But that's still a lot of work because we're extracting the float. We're going from like int registers to float registers. Instead, we can do something a little more interesting because we know that our value is two numbers that are packed. So what we can do is, that's becoming complicated. So first of all, we're gonna take our packed value. So we have two floats encoded in there, and we're gonna remove the sign. So if you're not familiar with how floats work, the topmost bit, so bit number 31, is the sign bit. If it's set to 1, the number is negative. If it's set to 0, the number is positive. So what we can do is say, so 1, 2, 3, 4, 5, 6, 7. We can, oh no, sorry, I want the opposite. So 7, 2, 3, 4, 5, 6, 7. So we're gonna take all the bits except the sign bit, right? So we're left with a positive, like the absolute value of the number. And then we can use a bit trick where we can say, we can subtract, sorry, I'm trying to remember, it's 7, I think it's this one. 1, 2, 3, 4. Okay, I'm gonna explain what it is. Yes, and 1, 2, 3, 4, 5, 6, 7. Okay, that's right. Okay, so that will work. First, we're going to compile that, and then I'm going to explain what the heck is going on. Explain Kotlin that Boolean. Why? Oh, I forgot to do the test. Equals. Let's see what I do. Return type. Expect actual Kotlin. Oh, yeah, can't put that on the new line. I'll put it over there. All right, so 14 instructions and 3 branches. Okay, and now we're down to 11 instructions, no branches. And you can actually see when you look at the values, you can see exactly what the code is doing. Interestingly, if you look at those values here, you can see that it's loading this constant, that constant. But because of the way ARM works, sometimes the way constants are loaded are with multiple operations, so it's loading like parts of the constant, multiple steps. Anyway, so the reason why this works. So first of all, we take the absolute value, so we don't have a sign. And then if you look at the way floats work, so I'm going to switch my window. So that's kind of useful information to know. Float.exposed. So there's a great website called float.exposed. It's a website where you can type float numbers and you can see their hexadecimal representations. You can see the bits they're made out of. Okay, so here this is a float, right? So at the beginning we have the sign bit, right? So if I flip it, we go from 0 to -0. So that's the bit that we got rid of. Then you have what's called the exponent. So that's kind of the magnitude of the number. And then you have the significand or mantissa. We're not going to go into too much details, but the way floats work, when the exponent is set to the maximum value, so all the bits of the exponent are set to 1, this is infinity, right? And if you flip the sign, you have plus infinity minus infinity. Now, any number, so if you take this infinity and you set any of the remaining zeros in the significand to 1, that's a non. That's not a number. So there's a lot of not a number. So the trick that we're doing here is to say, okay, we took all the bits except the sign bit, right? So we have we have all those bits to whatever they're set. Now, if we treat this number as an integer, right? Let's forget that it's a float, it's an integer. What do we notice? Infinity and all the nons are integer values that are greater than this value that I have here on screen, right? Like if I set any of those bits to the right as an integer, it's a greater value than this. So what we can do to check if our numbers are nons, we can take the first non value, so this number, right? So that's this 7f8 with a 1. And if I subtract that from the value that we have, like this v, if I end up with a negative value, that means that my original number was greater than this, right? And if it's greater than this, I know it's not a number. So we use this trick where we subtract it, and when an integer is negative, the top bit is set. So what we're doing here is we're saying, hey, if any of the top bits is set, then that subtraction yielded a negative value. Therefore, one of those two numbers is not a number. So a bit complicated, but the result is like the bare minimum we can do to test X and Y at the same time in one go without having to like go back and forth between between float and not a number. And then when you start thinking like that, you can do other fun tricks. So if I go back to the code, and I promise we're gonna like stop looking at such low level bit stuff for a little bit after that. Here's another interesting operation. Is my window back? Kotlin Explorer. Okay. So if we look at the unary minus operator, so this is you just want the negative, like the opposite value. So unary minus, if I say minus my offset, it's going to give you the minus x and the minus y. Third instructions, same thing. What it has to do is that it has to extract the two floats, take the opposite value of both floats, and then repack the floats inside the long. But we know that our floats they're encoded in a long, and we know that there's a bit that's the sign, right? So what we can do instead of doing that, we can do offset. We take our long, packed value, oops, and we can XOR, however you want to call it, the sign bit of both numbers. And now if we look at the generated assembly, so we go from 30 instructions and 5 branches down to, oh, look at that, 1 instruction. And the reason why this works is that, if we're basically, so we do a XOR of the sign bits in both floats. And so if the original sign bit was 0 and you XOR it with 1, it becomes 1. But if it was 1 and you XOR it with 1, it becomes 0. So basically we can flip it this way.
So I want to I'm going to say it live and it's going to be recorded. The first time I find something like this shit in one code base that I'm going to work on, I'm going to come to you. Because I don't care if it's fast. I don't care. Okay, who does that? What? Come on, really? How do you expect that I'm gonna understand this thing in 10 minutes. I mean, I don't want to give me 2 weeks.
Okay, so in the real code base, what happens is that those are all named constants that have documentation. The code usually I have like a few lines of comments explaining, okay, here's what's going on. Don't worry.
Have you ever worked with people? I mean, I'm asking. Have you ever worked in the real world with normal people? This is never gonna happen. This is just gonna be like a nightmare for every poor soul like myself.
I think a good solution could be having like an annotation. There's like, don't touch this code, and then you have lint that just yells at you if you touch anything. Like you put a checksum of the code in the annotation. And if the checksum doesn't line up anymore, then you get the build breaks. It's like, you need an adult to change this code.
Yes, a supervisor. Call your supervisor.
Yeah, but look, then when you start thinking like that, you can do a lot of cool things. So let's say you want to know if a float value is not infinite and not a number, right? It's just a regular number. So when you call the function that's part of Kotlin, it's called isFiniteOnFloat, and boom, like a bunch of code. We don't have to understand what it does. I'll show you. I wrote down the implementation. So if you look at the source code of Kotlin, this is how it's implemented. And it makes a lot of sense, right? It's like, it's an extension function, and it calls isNotInfinite and isNotNone. So pretty straightforward. But again, if you think about the way floats are represented, we know that regular numbers, if you take the float as an int, are all less than the value infinity. So we can rewrite this test by saying, hey, let's take the bits, let's remove the signed bit, and if it's less than positive infinity, then it's a real number. And is finite. Yeah, okay. Will that work if I do this? Let's see if this works. So 11 instructions, 3 branches. Oh, it's not an actual. Wait, I removed the wrong code. What am I doing? Oh, sorry. Okay, so let's bring back my function. There we go. So that's my function. Fast is finite. So 11 instructions, 3 branches, and now we're down to 6 because we're doing the minimum amount of work. And I wish that's the kind of stuff that the standard library was doing. Now,
I think that it's more like on a serious note. I don't think it's because performance, is more like because of maintainability. I mean, I don't argue that it's faster. I mean, because you have that's not, but you have to give it that it's a bit harder to read for the average.
Yeah, no, absolutely, it is, and that's why and again, that's where like commenting the code, doing this in the places where it is beneficial. I would never tell you to do that in code that's executed once or that doesn't matter. Again, if it's an inner loop and you really need to speed it up or you're targeting low devices, this is the kind of stuff that is good to know that you can do this and what tools can you use to get there, because you can reap the benefits, right? But then it's on you. Like, again, if I showed you, like, I had this, I wrote a blog post about this, but I wrote an approximation of the cubic root function. It's 4 lines of code. If you've ever heard of the square root approximation that was in Quake 3, it's a similar idea. It's like, you look at it, it makes no sense. Actually, I'll show you the code. So I'll show you the code, and then I'll show you the code as it is in the code base. That's going to make a big difference. Sorry, let me pull it up. Fast CBRT. All right. So here's the code in the code base. Let me put the function declaration. So that's the code. It's the cube root of a float, right? It starts by saying, hey, give me the bits, do an AND with whatever that value is, then add this constant that makes no sense to like this value divided by 3 and turn that into a float. Like, how the fuck is that? Pardon my language, but how the fuck is that a cube root function, right? Now, let me show you how how it landed in the code base. That maybe will make you feel better. All right, 4 lines of code, 130 lines of comments, right? Like, that's how you do it.
Yes, now I see. I see. Yeah.
Because otherwise, yeah, I agree with you. Like, you need
No.
You need to leave behind enough information so that the next person can understand why you're doing this and how you got there.
And I think the most important part is that why they don't have to touch it, right? Don't touch it, because this thing is has been made on purpose, like as fast as possible and as violent as possible. This is how it works, kinda. If you want to play around, maybe there are tests around the stuff. Sebastiano says we lock it in place, and it's a. But again, it's all about when you want to use it, and I'm not arguing the fact that it's like a million times in a for loop. Everything changes perspective.
But it's also a mindset, right? Because when you start thinking like that, again, without going down to this level, you start questioning the code. And I've seen many places in our own code or my own code where you're in a loop and you're not paying attention. You're like, hey, I'm allocating a new array every time it loops, or I'm creating an object that I'm discarding right away. It's like, you start like trying to find the shortcuts, and that doesn't necessarily make the code harder to read. Actually, sometimes it makes the code easier to read once you get rid of the craft. But it's just like, it's a good way to like put you in that state of mind. So to do something a little easier, right? Like, here's another piece of code from Compose. The differential of a Hermite spline, whatever, who cares? It's math, and it's pretty simple math. It's a bunch of like multiplications and additions, whatever. You look at the assembly code, 33 instructions, looks great. We load a few constants, -6, 6, 3, and 4, and then there's a bunch of multiplications and subtractions, right? What's wrong with this? Nothing's wrong with this. But by using, 6th grade level math, when you write down the formula and you factor, you're like, hey, look, there's a 6 and a 6 and a 6 and a 6 again and a 3. You're like, hey, it sounds like I could, maybe factor out some of those computation, right? You see like, 6 times y2, there's a 6 times y2 again here. Like, and once you factor the math, it has nothing to do with assembly or bit tricks or anything like that. And you compile this, so 33 instructions, refactor the math, and now 19 instructions, right? And we didn't do anything magical. It was just questioning what you're reading and realizing that compilers are amazing. I've seen R8, and I have a blog post about that. I've seen R8 take literally 150 instructions and turn that into a single constant by understanding what the instructions were doing. Fantastic. But they won't do this for you, right? And there are reasons because of floating points or whatever, but you can do this, and it's pretty easy to do, and it can pay off, again, depending on what you're doing. But if you're doing, let's say, image processing, right, or audio processing, you are helping the battery, you are helping the low-end devices. Sometimes it's also about just understanding what the hell the APIs that you're using are doing. So here's one of my favorite examples from the Kotlin standard library as well. Let's say that we have a function, and I don't know, color max, and it takes values that came from a color. So we have R, G, B, and and we want the max of those 3 channels. So we use in Kotlin, there's this function called maxof. It's great. You can say max of RG. All right, let's look at the code. Filing. Okay, fantastic. 2 instructions. It does the max of G and B, and then the max of that with R. Perfect, right? Now let's say that, oh, I forgot there's an alpha channel in my colors. Filing. Oh wait, because we optimize. We did the optimizations. So what was happening? Let's see if I turn off R8, or maybe it's because of the new versions of Kotlin. Yes. So if you turn on array, turn off array, what
What the
happens?
fuck?
Yes.
How? How did this go from 4 to 31?
And that's because if you look at the text code,
It's an
so let's
array?
compare.
Is it
Yes,
allocating
because yes, it's exactly what it
an
is.
array?
Because, right? Because what they did in the Kotlin standard library, they defined max of for maybe 1, but 2 and 3 parameters. And then for more than 3 parameters, it's a var args,
It's a var,
right?
yeah.
var
Okay.
the array. So
Yep.
suddenly, if you're not using array, you did this thing that looks super innocent, and you're like, oh wait, I'm allocating every time I call this function now. And I'm invoking a static function instead of doing 3 instructions. That's all it is. It should be 3 instructions. And by the way, we're not seeing the cost, like, because here it's calling that function. You're not seeing the cost of that function because that's a loop. So there's also like more code running after those 30 instructions that we have in our code. And that, for instance, I caught, like, there was a question at the beginning in the chat. The way usually I look for this kind of opportunities, let's say, I like to start by looking at allocations, right? In Android Studio, there's the real-time allocation tracker. I do something simple like scroll a list, and look at the allocations. And then I just go through the list of allocations and I look for anything that looks suspicious. And when you see, why are we creating a bunch of arrays? You look at where they're coming from and you're like, why are they being allocated in code that does, this? Like, wait a minute.
There's no array there.
Yeah. And so, it's not the only way, but it's usually like a good way of like pointing you at code that probably is doing more than it should, because an allocation is very often a good indicator. Not the only one, but it's a good one. Let's see. Here's another cool example that I've seen recently. Let's say that we want to, speaking of arrays, let's say that, I don't know, we want to create an initialization function, takes a size, and it gives you an int array, and we want to make sure that everything's initialized to 0. Cool, right? Like, create an array, here's the size of the array.
This one I know.
Yeah. So this one's fun, and there's no one to blame. Here we go. 48 instructions, 13 branches. What's going on?
I mean, what's going on here?
So that's because, the code completion here is a bit at fault, because when you type that in the IDE, it's of this constructor that takes your lambda to initialize the values inside, right? So like, okay, so I want 0, so I'm gonna initialize to 0. But the contract on the JVM or on Art is that when you create an array or any variable, it is initialized to 0. You don't need this. And if you remove that, if you remove the loop that's going over the array and that's reinitializing everything, and that's what it looks like. That's what it should look like, right?
So this sounds more of a lint check sort of thing.
So I told Tor, and I think Tor was working on one. But again, like, it makes me sad that we need a lint check for that, right? I kind of want the compiler to like.
Yeah, but the compiler, I mean, array is managing it. I mean, even if you put 0 there, is it array helping or?
All right. Well, let's see, right? Like, so if we go back to the original code, so I have array turned on right now. So let's say, so that's with array, so 48 and 13. Now, if I turn off array, let's see what happens. Maybe worse, maybe the same. We'll see. Compile. Looks like it's exactly the same with array. So
this is that's the thing. That's unfortunate. This is unfortunate, right?
Is about the memory model, multi-threading. There are things that you know about your code, and I'm going to show you an example of that a compiler can't assume because of the rules of computers. So let's look at matrix, right? So it's a matrix class from Compose. It's an inline class. It wraps an array of 16 floats, right? It's a val, so can't touch it, can't reinitialize it, it's always going to be an array of 16 floats, right? So if I compile that code, we have array turned on, boxing, whatever, constructor, let's see, where is the reset? Okay, 30 instructions, 2 branches, and one of the branches, it's what I was mentioning earlier. So there's a test at the beginning where Art is checking, okay, it looks like you're going to access 16 entries. So if the array is less than that, we're going to jump to this de-optimized code path that's going to throw the array index out of bound exception. But the reason why, but you look at the code, you're like, hey, Art, no bound check. Like, we know the array is 16. Those are constants. Like, I cannot have an index out of bound exception. It's not possible. Except in the world of a compiler, there could be a piece of code in C that reallocates that. There could be JNI, there could be a reflection, who knows, right? Like something somewhere could mess with this array, even though I know that I'm not doing that, but the compiler can't know that. So interestingly here, the trick, and it looks really silly, right? It's to say this, if my array is less than 16, bail out. And you're like, wait, that's dumb. Like, it's never going to be true. Now let's look at the code. So 30 instructions, 2 branches. Look, 23 instructions, 1 branch. Because we're basically telling Art, we're telling the compiler, we're telling Art, hey, trust me, no bound check is necessary after this. I've already done this. So unfortunately, it's very limited. Like if we had like an offset, if every one of our access was written like this, I haven't found a way to help Art figure out that it doesn't need the bound checks. But if you look at the matrix code, and again, there's a comment before every one of those checks, every method now in matrix starts with this, and it dramatically reduces the number of instructions in some of those functions. There's only one left, it's this less than, it's the one that we wrote. So it loads the array, we compare the size, and everything else is just storing the value in the arrays. It's exactly what we're supposed to do, nothing more. So that's where, like, yes, you should trust the JIT and the compiler, but you also need to understand their limitations. They can be magical, but there are things that they will not and cannot do for you.
I guess there are some things that are, let's say, easier to figure out by looking at the source than they are probably by looking at the bytecode, right?
Yeah, and that's where, like, that's why, I built the tool this way, where you can look at the source, the DEX, and the assembly codes, because it's how you piece together that puzzle of, like, okay, what is going on? Why is it happening that way? And very often, I can see in the assembly we're doing too much, but like trying to understand, okay, it's only by looking at the DEX, I'm like, oh, okay, that's what's happening. Therefore, if I remove this, or if I rewrite this operation differently, then the code's going to be better.
Out of curiosity, do you think that the IntelliJ is gonna flag the line 8?
It doesn't.
Okay.
It doesn't, either because they didn't write a check for that, or same reason, because they can't guarantee that
they can be sure.
Right? Like, I can guarantee that. Now there are ways to, like, make this even faster that I'm not going to get into with this infamous sun.misc.unsafe that I may or may not start using soon. But there are other ways to even improve that. Because the way you could speed that up, for instance, if I were doing native code, we were talking about bitpacking earlier. I'm like, hey, look at this value 2 and 3, right? I'm setting 0, and they're both floats. But if I could access the memory as longs, I could set those 2 values at the same time by just telling the CPU, hey, put 0 in that 64-bit address. And do 1 store instead of 2, and we could literally have half the number of instructions here to go faster. But Java doesn't let you, and Kotlin don't let you do that. You can't alias the memory unless you use some interesting private APIs. All right, so if we go higher level, here's another one that's interesting: collections. Java and Kotlin come with a lot of very powerful collection classes. A very popular one is map. So here I wrote a very simple function, right? It's like, takes a map, we're just gonna iterate over the entries, and we're gonna return, it's really stupid, but it's gonna return the sum of the length of the key and values as strings, right? It doesn't matter. Like, all we're trying to do here is to iterate over all the entries to see what happens. This is something that we had to do in a lot of places in Compose, especially in the Compose runtime. We use hash maps a lot. And when you look at the generated code, there's a lot of code here. Might be okay because it's a hash map, so it's complex thing. But if you look at so BLR in ARM, it's branch with link to register. So that's basically a function call when you see one of those. And you can see here it's trying to tell you like where it's going. So here you can see, okay, we're getting the entry set. That's this dot entries. And then you can see that, oops, we're creating an iterator. And then we're doing has next and next on the iterator. So lots of function calls, but more importantly, and then get key, get value. So lots of function calls, pretty expensive. But more importantly, we're creating objects. If we were to look at this piece of code in the memory profiler, you would see we would allocate an iterator every time, which is not great. And we get even worse, right, if we had primitives in there, because there would be boxing and unboxing happening. So to work around that, because we don't like allocations in Compose, not because allocations in themselves are bad, because sometimes they're very necessary, but again, it goes back to when we do this as part of like high traffic code, like the slot table, for instance, in the Compose runtime, or layout or rendering, creating all those objects, costs CPU time, but we're gonna have GC running. And even if the GC right now can happen on a thread, that's battery, that's a core that we're using to not do something else. And on other devices, you could have like long GC pauses because we have accumulated a lot of garbage. So we don't like allocations. So now I'm gonna copy paste a lot of code because that's a new hash map that's part of the AndroidX collections library. If you're interested, we can look at how it works. It's actually pretty cool. Ported that from another Google library called Absol in C++. But what's interesting is that if we look at the same function, so our sum, right, using this hash map that's called scatter map. Looks like a map. Okay. It looks like a map, works like a map. It does not implement the map interface for specific reasons, but it's optimized for never allocating. It will never allocate unless it needs to resize its internal storage. Okay. So the same code here, right? Iterating over all the entries. It's just map.forEach. You pass a lambda, it gives you the key value, so you don't have to do destructuring. And if we look at what it does, that's going to take a little longer to compile. So we had like 107 instructions, 2 branches. So we have 92 instructions, so fewer instructions, more branches, but we're not invoking functions. All the code, if you look at the code, all the code is inline. Like that's the entire for each, not a single function call. There's no allocations. If you look at the instructions, it's all very basic stuff, and it's much faster. I don't remember the number. I have the numbers here. Let me see. So to give you an idea, compared to a regular hash map, yeah. So on a Pixel 2, iterating over 1,000 elements is twice as fast.
Jesus. Okay.
And that's not taking into account the cost of whatever garbage collection might come because you've allocated. And then the other aspect of this is, and we can talk about that. Every time you insert into a standard map, there is an allocation, right? You have your object, you insert into the map will allocate an entry object that wraps your object. Scatter map does not do this, no allocation ever. And same thing, inserting 1,000 elements is twice as fast and doesn't allocate anything, so there's no GC. So yeah, and that's also the kind of stuff where, there's a lot of places in your code where like it's nice to be able to use like a standard interface or receive a standard interface. It might not matter, you're clicking on a button, the latency can be high, that's fine. if you're doing this kind of stuff, like like we're doing inside measure layout, semantics, accessibility, pointer dispatch, you really want to go as fast as you can and be cheap. And that's why like AndroidX.collection has a number of collections. So we have scatter map, there's a scatter set, we have the ordered scatter set that preserves the insertion order, and then we have combinations. We have scripts that generate all the possible combinations for primitive types. So if you want a map of like float to object, object to int, we have all the variants. So you can also not box and unbox. So we have like, we try, it's always a compromise when you write a collection, but basically we try to eliminate all the extra work as much as possible. We also have the for lists, we have object list, that's an array list that's slightly faster. We have int list, float list, stuff like that, that are super useful.
Do you so I know that the for each function, because it's a function, it is generally more expensive than doing a simple loop. But then again, I know that loops in Kotlin are a bit weird.
Oh, you mean the for each here?
Yeah.
So the good news that those are inline functions because they take a lambda. So to avoid allocating the lambda, that's an inline function. So it's not, it's just like a loop. The difference that here, it uses an iterator, but this one, I mean, if we go look at what that function does.
Because I don't think you, like in the fast way in Kotlin to do a for is to do a while with an index, right?
That depends. They fixed a lot of the. I'll show you an example where it's still not fixed. But the basic case is fixed. But in scatter map, for instance, for each, so it's an inline function, takes a lambda. Internally it calls for each indexed, and that way basically we have indices inside an array, and that's how it fetches the key and value. And for each indexed itself is an inline function. And what it does, we're back to weird bit stuff. We're doing weird bit stuff. It's super interesting. Like if you're interested, you could go read the source code. Basically, it's able to look at 8 entries at a time to find, like when you're doing a get, like you're trying to find the value for a key. It's using like longs to like be able to find like your value like super fast. So it's pretty cool implementation. Again, came from C++, a library called Absol. And at the bottom, it goes back to what you were saying earlier, what we were discussing earlier about comments. Like for instance, this piece of code, this group function, 3 lines of code, lots of comments explaining why, like why those lines. Anyway, lots of interesting stuff in that file. But yeah, so for loops, let's see if I can recreate the problem.
Before we move forward, can I say that, I mean, for how cool is this stuff and how easy is to use, because, well, there's plenty of permutation, more types, things, and it's pretty much everything is documented. There is a huge discoverability issue for the library because I never heard about this thing,
but that's why it's here, right? It's
but that's,
so now you know.
Now I know, and I hope also a lot of people know after this. But this could be very meaningful for some people that are working with very specific domains, right? You need this kind of, I mean, you say it's the speed of a hash map in just like a random scenario. So, I mean, twice the speed is no joke.
It's no joke. Well, actually, it's better. And actually, maybe I'll show you something and then we'll get back to it because it also uses less memory, which is cool. Let's see. So here, let's do something silly, right? Like we have a function. We want to print the squares from 0 to n, regular loop. It's fine. Looking at the code real quick, there's nothing bizarre going on. You can see that branch, the loop is somewhere in here. we're testing if we reach the end of the loop. So regular loops work fine. Now, and let's hope that the prime is still here, which is a weird thing to hope for. But let's say we want to only look at every other element. Oh, that's been optimized. Let's see if that's all right doing that. So that's optimized, so that's good. Yeah, that's all right. Okay, so all right.
Thank you,
we
Ray.
agree. We agree. All I did, right, was to say, hey, I want to increase I by 2, right? Like in Java, you would say like I equals 0, I less than n, I plus equal 2, right? That's should be free. Not so much in Kotlin. As soon as you write step, it allocates a freaking progression object. Oh wait, no. In this case, let's see. Is it able to? Did they optimize that? Okay, that's good. It looks like they optimized it. But okay, they optimized it because that's good. Yeah, because they're invoking. Okay, so we're invoking a static function, but at least okay, no, that's good. It's actually computing the increase that you want. But it used to be in older versions of Kotlin, so be careful if you use older versions of Kotlin. It would create a progression object and do a while loop. That was basically an iterator. So it was allocating objects to step over the array, over the range by 2 instead. And it was even worse. Even if you did step 1, which is the same thing as not stepping, it was creating objects.
It's a good thing they fixed that.
Well, I mean, now the question is, did they fix it after your blog post?
I don't know. It doesn't matter. I'm just happy that it's been fixed.
Fair enough.
But it took several versions of, and to Sebastian's point, like it used to be that even because there's a number of ways to loop in Kotlin, right? You can do 0.10 for each. You can do like the actual for loop, and depending on the one you picked, the generated code could be really bad or really good. And nowadays, like based on that, apparently now they're all good, so it's great. Yeah, so if we go back to the hash map, I'm gonna real quick show you slides that show information. Let me. Sorry, I'm trying to find the diagram because it will be easier with the diagram. Let's share my window. Okay.
It's still Kotlin Explorer. Oh, no, now it changed. Okay.
Okay. So if you look at how, when you do mutable map of in Kotlin, it always creates a linked hash map. I know some folks will disagree with me, but I don't like that for one reason, because linked hash map preserves the insertion order. So when you iterate over the map, you have the same order that you insert into the map. And my issue with that is it can create several bugs if somewhere you have code that relies on that insertion order without realizing it does. I have seen that before. On top of that, linked hash map, because it has to preserve the insertion order, is more expensive in terms of memory. So if you look at how linked hash map is implemented in the standard library, you have a table. It's an array of nodes. It's an array of entries, and those are your hash map buckets. I'm sure you've heard of this kind of stuff. And then in the bucket, you have those linked hash map entries. And this is what's stored in an entry. You have the key, the value, so that's the bare minimum we have to store. There's the hash of the key, like the full hash. And then you have 3 other pointers to like other linked hash map entries and to nodes. I don't know, like next, like I forget, someone told me why, but there's before, after, and next. I don't know why after and next, how they're different, but you need that. It gets even worse because depending on how many entries you store, the hash map, the linked hash map, would change its implementation under the hood. And it will change to this tree hash map that has even more stuff in there. So we have after, next, and now you have prev, and there's also left and right, and there's a parent.
Red.
Anyway, so when you
red. Oh, let's throw red there with the
that's
color.
yeah, because that's a red and black tree,
Fair enough.
Google.
Yeah.
And so when you iterate over the hash map like we were doing earlier, that means that you need to go read like the head to be able to find the first node. Then you have a pointer, you jump somewhere else in memory. You're going to read your key and value, then you're going to read the next node, and then you're going to jump somewhere else in memory, and you're going to keep doing that. And once your app has been running and memory is kind of like shuffled around because you don't allocate all your entries at the same time, or the garbage collector might move stuff around, you're going to have a lot of cache misses, and you're reading quite a bit of data. So it's not efficient for the memory cache. And on top of that, that means if you do the math, the overhead is 30 to 49 bytes per entry. So let's say you want to store just booleans in your map, you're paying an extra cost of like 49 bytes maybe per boolean, which technically could be 1 bit, right? So on a small hash map, not a big deal. But once you start storing, thousands of elements, I mean, this adds up, right?
Yeah. This is enums all over again, isn't it? in 2 years, we'll be like, oh, now you have like 50 gigs of RAM. It's fine.
It's okay.
The way the scatter map works is that there's an array of keys, there's an array of values, and there's an array of what's called metadata. The array of metadata is interesting because it's longs, so each long actually maps to 8 entries for the keys and values. So the overhead we have in scatter map is 1 byte per entry, not 49, just 1. Wow. So, and also that means when you iterate, the reason why it's so much faster to iterate over, if you set aside the allocations, the reason why it's faster to iterate over the scatter map is because we can just literally go over the arrays in order, and it's going to be extremely cache friendly for the CPU. And we can easily test, whether an entry is empty or not. We have the metadata information for that, so it's super cheap. And there are ways to build hash maps that's even better for that, specifically for the for each. And that's what makes it so much faster.
So we're gonna have a for each scatter map soon.
Yeah, I've been thinking about this.
Of course.
I want benchmarks though.
Yeah. Well, actually, I also wrote instead of the LRU cache, there's a new cache in AndroidDev collection called sieve cache that's based on scatter map plus a new recent technique. There was an interesting paper that came out this year, I think, on how to handle caching policies, like the concept of LRU, like least recently used. Mm-hmm. It's doing it slightly differently. It's super cheap and super fast. So it's awesome.
You really are a graphics programmer at heart, because you reference papers, and I'm like, yes. Yeah, that's blue. I like it.
Yeah.
But yeah, and again, there's a lot of situations where like it's not going to be. You don't need to use scatter map, but it can be faster. It can use less memory. It can be a bit more expensive when you remove elements one by one compared to a regular map, because it has to do more management of the arrays instead of just removing nodes, which is super cheap. But if you have performance-sensitive code, or at least you don't want GC, you should really look into using the AndroidDev.collection classes. They're super helpful.
We need to push the discoverability of this stuff.
Because, and so someone
people need to know.
Yeah, so Simofonov is asking, why not directly change the normal HashMap map? The main reason is the semantics of the interfaces of the standard map. The reason why scatter map does not implement the map interface is because the map interface forces you to implement, let's say, dot entries or dot keys or dot values, and those return entry sets and value sets that are themselves objects. And to iterate over those objects, you need to call dot iterator that creates an iterator. So implementing the map interface would funnel you into the code path we want to avoid. Like for instance, in Kotlin, if you were to do dot for each on our scatter map, you would have an iterator because that's what the standard library will call on the map interface. So it can be a bit cumbersome because you can't use it as a regular map interface. What it does, however, it has a asMap function on scatter map. If you call that, it will create an object that behaves like a map and that delegates to the scatter map. And read the documentation, it explains why you should use it and maybe you should cache that object. And we try to optimize that object as well, but it will behave like a map interface. And on top of that, there are some things like the for each, for instance. We saw like the for each is fully inline. We play tricks that are a bit dirty. If we go back to the implementation, we do things. That's where we try to be pragmatic in Compose as much as possible. We're very careful about compatibility and APIs, but sometimes we may make sacrifices. Let's see. Are we going to see my? Yeah. Okay. If you look at the implementation. Scatter map. Yeah, so all those arrays that I mentioned, they're internal, they're not private, and they're published API. That means at the bytecode level, they're actually public. And we had to do that to be able to make the inline functions as fast as possible so that they can access the array directly. So technically bad, we don't mind because you're gonna, this class is meant to be used from Kotlin and Kotlin only. So in Kotlin, you're not gonna see those things. If you were to use Java, I think you would see them maybe. But that's
also who cares? I mean,
yeah, no, exactly. And again, the goal is like the API itself. When you use the scatter map, the API is nice, right? Like you have your .any, like we try to recreate everything that comes, like you have get or else, you have all, any, get or put, count, like all the things that you expect to find on the map, they're there. And very often I think, when you optimize code, that's what I like about Kotlin. And I'm going to show you one last, like another example that's actually pretty cool. So I'm going to jump into the actual source code of Jetpack Compose. I don't know. It's right here. And this is the code I fetched from AOSP. So there's no code that's secret. I think was it in Velocity Tracker? Yes. Okay. So Velocity Tracker, that's a class that when you fling your finger. How do we increase the font size?
You can do ID zoom as an action if you want.
Yeah, I'm just gonna do the only way I know. Yeah. Okay, so Velocity Tracker, when you do a fling, on a list or a scroll, that's the code that's responsible for computing how fast the list should scroll and animate. Won't go into the details about the implementation, but somewhere in the implementation we make heavy use. There's this least square polynomial fit. Anyway, and it uses matrices. You're like, okay, cool, a matrix. It's nice. There's a matrix object. We can index it. Like in Kotlin, you can have an index operator that takes multiple parameters. So you can index the matrix like you would in math, right? So you have like row and column. Looks nice, easy to use. We have a dot product that you can call. Pretty cool. Now, the original version of that code had an actual matrix class that contained an array of arrays, actually an array of vectors, and a vector was a class that itself contained an array. So when you think about it, you're like, I have a pointer to a matrix, then a pointer to an array, then a pointer to a vector, then a pointer to an array, which meant that all those accesses were actually pretty expensive because we kept jumping in memory, and we could have cache misses. Now, what's really cool about Kotlin is that if we go look at the definition of matrix, it's a type alias. Our matrix is just an array of arrays.
Okay.
And a vector is a type alias of a float array, right? And then using extension functions, we can add a get operator that takes a row and column to the matrix object. And it directly taps into the array. And it's really cool, right? Because the code is optimized. We don't allocate things we should not allocate. We still allocate arrays, which I'm a bit bummed about, but whatever.
Man, at
But-
some point.
Yeah, but the ergonomics of the code remain the same, right? And that's what matters in the end. It's like, is the code easy to read and to use? And that's what I love about Kotlin. We can write code that's highly optimized, but that still looks and feels really nice to use. If you go to on my blog, I wrote a blog post more specifically. Leland and I were working on an interesting problem about how to do like efficient spatial queries of rectangles. And I wrote a blog post to show like, look, I have this really nice to read and write code. Actually, let me just find the blog post. That's going to be easier. Where's my readability of Kotlin?
I like the extensive use of the shut up annotation for the nothing to inline.
Yeah.
Yeah, it's also highlighted because the IDEs probably say, "Oh, but you don't need the suppression," and then you take the suppression away, and then the IDE says, "Oh, you shouldn't do."
You should do this.
Anyway, so here's the code. The idea is that you have a grid and it looks, it's a grid of occupancy. So either a cell is empty or it's full, right? It's 0 or 1. Pretty simple. There's a grid object, whatever. The way it was implemented, it looks like this. It's pretty scary. It's a lot. Look at that shit. Like, look at this rasterize. That's the function that prints the grid. It's like,
okay,
whatever, right? It's a bunch of dark magic.
Sure. I mean, I don't even know rasterize. What's the meaning? I don't even know the
printed to a string in this case.
Yeah, basically it's print to a string. Anyway, but what's really cool is that then we add operators and the concept of a rectangle. So the way you use that code is still really nice, right? Like you create a grid, and actually what that function does, it returns a long. A grid is not a thing. It's just a long, right? It's an inline value class, so it's just a single long. So that doesn't do anything. A rectangle is also long, and when you add it to the grid or you subtract it, the way it's implemented is more dark magic of bit operators. So it also doesn't really do anything. You can have a for each, right? You can say for each occupied cell, run this lambda, some more dark magic of bit operations like shift and end, whatever, it doesn't matter. Oh yeah, look at that. For instance, actually there's dark magic in the dark magic where cells, so that's a long, that's how the grid is encoded. And we say, oh, has next. We're using the long as an iterator.
Oh God!
Right? What the fuck is wrong with you?
But that's cool because you're
yes, but
right.
So who does that? Okay.
Well, but the code is really easy to read. It's like as next. You're like, okay, I get what it's doing. But the way it's doing it is weird.
Yeah. No, I like the API. I understand the fact that the API is nice.
It's just don't open the bonnet.
Yeah, don't touch.
Right,
don't
and so
inside.
In the end, what you have is like, okay, I can write code like this. I create a grid that has a rectangle. I can do the union with another rectangle. I can then find the intersection with yet another rectangle, and then I can process every occupied cell. The code looks really good.
Yeah, the API is nice. It's
that's the assembly code that's generated.
Okay. Wow.
Right?
Okay. Because you're doing things so at low level, so manually, but not just so magically that it ends up being very.
But more importantly, we wrote the code in a way that's friendly to the compiler and the CPU, and so it has applied a bunch of optimizations to get to that, and it's awesome. And my favorite example, is in the end it's this thing. I have a grid initialized with a rectangle, and I do the union with another rectangle, right? All those things are constant, and we've seen the code before, right? There was a lot of bitshift method calls. There's a lot of stuff happening. You feed that through R8. Okay, so before R8, those two lines of code, that's what gets generated, right? That's what the Kotlin compiler will do.
Yeah.
Because it's all the code that you wrote. 111 instructions, bunch of function calls, whatever. You run R8 on it, here's what you have.
Wow.
This is literally R8's that's the grid. Because we wrote the code to be simple, and therefore the compiler can understand it, and it's able to all those ors and ends and shift, it did them at compile time and got rid of all the code. And it's awesome. So
this is impressive.
So, and again, that's the curse of compilers. They can be so impressive, right? So magical when you see that. And sometimes they're like, nah, your array that's always the size of 16, I don't trust you. I'm going to check every time.
Yeah.
I think there's one last question, and then we should probably wrap up because it's getting very late. So this is all optimized for ARM64. What happens on RISC-V?
Yeah, so
x64?
Yeah, I haven't tested on RISC-V. I've looked often at x86. x86 is not really something that I care about, honestly, because aside from the emulator, like that's not really a target for Android. But the reality is, all those CPUs, they have more or less the same capabilities. So especially when you write code at a high level, like we do with Kotlin, if you can get it to be nice on ARM, it basically will be nice on other platforms. And if it's not, it's not really about what you wrote. It's more about the backend of Art, for instance. So I wouldn't worry about it. Now, if we were to write C++ code by hand and use assembly instructions directly ourselves, different story. But yeah, it's going to be fine on other architectures.
I was wondering about x86, for example, because it's theoretically it's a RISC architecture instead of a CISC. But then under the hood is still a CISC, so I don't know.
Yeah, well, and also like what is RISC and what is CISC nowadays? Like it doesn't. I mean, if you saw some of the operations that ARM lets you do, they're ridiculous. It's literally like compare those two values if they're not equal, and then select one of the two values but shift it by 32-bit, and that's one instruction. So it does multiple things. So
I'm sure it's needed for like some crypto or some video decoding or whatever like that.
But it's also used like in some of the code rewrite, like it ends up being like folded, like the code gets folded and you have fewer instructions and it's awesome.
The compiler is like, oh, wait. I know what you're doing there.
Yeah, I can use this. Finally, right? Oh. And it has this. I imagine the compiler with this box of instructions that it never threw away, and finally can use one instruction.
It gets better, for instance, on the GPUs. On the GPUs, when you realize that when you do something like, something dumb, but let's say you do minus x times 8 plus the absolute value of y, that becomes one instruction because the GPUs have instructions that are literally, load this value, load the absolute value of that register times 8. That's one instruction. It's like, because it's so common in graphics that I'm like, we're going to optimize for that. So yeah,
crazy.
Modern CPUs are pretty cool. And ARM, like when you look at the disassembly, there's a lot of what I see in the disassembly I don't fully understand. Like you can kind of guess what it does to an extent. But it's not scary, and also art tends to use the same instruction. Like it's 95% of the instructions I see are always the same things, like load a value from an address, store a value at an address, multiplication, addition, subtraction, jump somewhere else, right? It's more tedious than anything, but it's nothing complex. But honestly, it's almost easier to read sometimes that, like fancy flow or functional code that just like you're like, oh, it's a map of a take of an if of a for each of us. Like, what does it do at the end? And so it's not. It's simple. It's scary, but it's simple. So don't be afraid. And it's also just interesting to like do this from time to time to get an idea of what the compilers do or do not. And also art, right? See what art does for you and use art. Like,
if there's one thing that is important from today is enable array. If you haven't done it, do it, because it does make a difference and it costs you nothing.
Nothing, yeah. The takeaway is enable array.
You don't need to use the special collections. You don't need to care about the bytecode. Just enable array, right?
Yes, I agree. Yes, no, I know it can be difficult, especially with if you use libraries that do like GNI or reflection, but it's worth it if you can make it happen. It makes such a difference, and and I like its main job is to shrink your binary, but to get there, it optimizes the heck out of your binary. Now, one thing I should add, where you have to be careful. So, the reason I use inline so directly is because Art will inline your code sometimes up to a point, either because the function is too long, there's a threshold, that's fine, but because Art wants to shrink your binary, I think the threshold is 5. So if you invoke a function more than n times, let's say 5 times, it will stop inlining it, because then your code starts growing.
Yeah, because the copy paste gets over the speed.
But sometimes I'm like, I don't care about the binary size. I just want that code to be inline, because when you inline, then the compiler can also do more optimizations, because the code is shared with other things. And so
is that when you start having inline functions that call inline functions, so that
but that's why using tools like Compiler Explorer online or Kotlin Explorer on your desktop, be careful, have benchmarks, measure. Sometimes I get out of my way to call the same functions multiple times to see, okay, does this change anything? Am I doing the right thing? And I'm pretty sure I've made mistakes, because I'm never looking at the full application, because the kind of code I'm looking at, if I had to find it in an APK after it's been inlined, I don't know. Sometimes I do this, but not for everything. So that's why I use the tool, I find my optimizations, and I validate them with benchmarks, and that way I know that they did something.
Nice.
Enable alert.
Enable alert.
So we are running out of time,
yes.
Otherwise Twitch is gonna yell at us. So Romain, thank you for this deep dive in. There's a lot of nostalgia from the old days at the university when we were doing this.
Always a pleasure. But and that's also where, just to wrap up, understanding a little bit about computers, right? The concept of memory caches, instruction cache, data cache, stuff like that. It is helpful. You're not going to use it all the time. I had an example in the slides I showed where one of the simplest. Okay, one last slide. I know we're going to get to that, but one last slide. Sorry, let me bring
That's
it back.
how you can tell Romain is passionate about this. I have one more slide.
Well, because it was one of the most efficient optimizations I've done for the smallest number of characters typed. And there's no dark magic in it. It's just the simplest thing imaginable. So that was from the code. Is it visible? Not yet. Okay.
Yes.
So that was the code that we use in CI. So it doesn't run on the device, but it runs in CI to compare, to do screenshot testing, right? So we want to compare bitmaps. We have a reference image, we have a bitmap. So more or less the code ended up being that, right? We have an array of pixels, whatever. We want to iterate over all the pixels, X and Y, find the pixel, and then compare it to another value. Here we do a max, but it doesn't matter. That was the idea. We go over all the pixels. Can you spot the problem, the performance issue in that code?
No.
You have 2 iterators?
No. It's see how we iterate over the x-axis first, then the y-axis?
Mm-hmm.
You want to do it the other way around.
Oh, because it's smaller.
No, because the way bitmaps are laid out in memory, we store them row by row. So what was going on, so basically, so you imagine if that's your bitmap, when you iterate over x first, you're gonna look at this value, then that value. The problem is that the way the CPU works, when you read that value, it's gonna prefetch the values next to it. But then you're gonna go far in memory and say, no, I want this one, and the CPU's go, I'm gonna prefetch that, and you're gonna have a cache miss for every
single one. Wow.
Right? And so that, if you benchmark it, you have the number. I think I have the number somewhere. Where's the slide? Sorry, I have to play the presentation. So on the Pixel 2, doing that is literally 5 times faster by just swapping the X and the Y.
We don't see anything right now.
Oh yeah, no, I know. I just looked at the number.
Okay.
Anyway, so it's 5 times faster by just swapping the X and the Y. That's all. And to get there, you have to understand just a little bit, right? How CPUs work. It's helpful. And that goes back to the reason I optimized the hash map was because, we have a bunch of jumps, that's bad for memory, so let's find a different way.
Yeah.
And now I'm done.
Chapeau.
Beautiful. Beautiful people. Thank you again, Sebastiano. We are streaming next week, right?
Yes, we're gonna have John, and we're gonna be talking about paparazzi too.
Ooh, that sounds
Nice.
fun.
Well, I mean, we are
Speaking
calling it
about
screenshot
comparing
testing.
bitmaps.
Yes,
Yes.
screenshot testing,
Yeah.
right?
What a
Make sure that he's iterating over them in the right way.
We'll tell him. We'll tell him. We'll make sure it's like Romain said.
According to my last guest.
Thank you
Oh.
again. Have a
Yeah,
great
thanks.
day, afternoon, evening, whatever time it is for you, and we'll see you next week. Bye.
Ciao.